Imagine if, the starting point we use for understanding global warming, the point before things really took off because of human activity. What if that starting point wasn't quite right?
Not completely wrong, maybe, but perhaps missing a crucial early piece.
Exactly. And maybe because of that, we're actually a bit further down the warming path than we generally think.
That's precisely the provocative idea coming out of some really fascinating new research. And it uses a source you probably wouldn't expect to reconstruct climate history.
Right. Sponges.
Yeah.
Today, we're doing a deep dive into this cutting-edge study that uses marine sponges as like a natural archive to get a clear picture of past ocean temperatures. Our sources are the actual research paper. It was published in Nature Climate Change, and also a helpful summary from the University of Western Australia.
And our goal here is to unpack this. How can a sponge possibly tell us about climate history? What does its record, stretching back centuries, actually reveal about when warming started and how much warming has occurred?
And crucially, what does all this mean for where we stand today relative to those big climate targets like 1.5 degrees Celsius and 2 degrees Celsius?
And yeah, the headline finding, the one that really jumps out.
You ready for this?
This new data suggests industrial era warming kicked off earlier than we usually assume. And because of that, the total global warming we've experienced is already maybe half a degree Celsius higher than some key estimates, like those from the IPCC, which rely more heavily on those instrumental records.
Half a degree. Okay, we have to dig into how they figured this out. How does a sponge become a climate historian? It sounds a bit like science fiction.
It does sound pretty wild, doesn't it? But the organism involved is a specific type called a sclerosponge. The scientific name is Ceratoparella nicholsoni.
Sclerosponge, okay.
Think of them as really old, stony, reef-building sponges, not your bath sponge.
Gotcha. And where they live is critical for this study, right? These ones came from the Caribbean.
That's right, around Puerto Rico and St. Croix. And importantly, they weren't living right at the surface. They were collected from depths between about 33 and 91 meters.
Okay, and that depth puts them in a specific zone.
Exactly. It puts them right in the ocean mixed layer, often called the OML.
The OML. So what is that and why is it important here?
So the OML is, well, it's the upper layer of the ocean that's actively mixed by wind and waves and currents. Down to a certain depth, the temperature is pretty uniform because of all that mixing.
Okay.
And the key thing is, because it's a large volume of water, not just the very surface skin, it has more thermal inertia. It doesn't fluctuate quite as wildly as the absolute surface temperature. It gives a more stable, sort of integrated picture of upper ocean heat content.
A better buffer against short-term noise.
Precisely. And the Caribbean OML is a good spot to look for global trends because its temperature is mostly driven by large-scale things, like greenhouse gas forcing, rather than, say, complex local currents. Though it does still pick up big signals like El Nino.
All right, so they're in the right place, a stable place, to record temperature. But how do they actually do the recording? That's the amazing part.
This is where the chemistry comes in. So these sclerosponges, they build their skeletons out of calcium carbonate.
Like corals.
Similar idea, yeah. They use a form called aragonite. And they grow slowly, adding layers over hundreds of years.
Okay, layer by layer.
And as they grow, they take elements straight from the seawater around them and build them into that skeleton. Two of those elements are strontium senior and calcium ket.
Strontium and calcium.
And here's the trick. The ratio of strontium to calcium that gets locked into the skeleton depends on the water temperature at the time the skeleton was forming.
Ah, so it's like a built-in thermometer.
Exactly, a paleothermometer, as scientists call it, embedded right in the sponge's structure.
So the researchers, they collected these sponges, sliced them open, like tree rings almost.
Kind of like that, yeah. Thin sections. Then they analyzed that solution ratio in tiny, tiny steps along the direction the sponge grew.
And they can date each layer.
Yep. Using techniques like uranium series dating. It relies on the radioactive decay of elements to pinpoint the age of each bit of the skeleton very accurately. So you get a chemical signal, the Sirkiki ratio, tied to a specific time.
Giving you a temperature timeline.
A continuous temperature timeline going back centuries. But of course, you have to check if this sponge thermometer is actually accurate.
Right, how do you calibrate it?
They compared the Sirkiki ratios from the most recent layers of the sponge, say from the mid-1960s up to near the present, against reliable modern thermometer readings of sea surface temperature for the same period. They used a standard data set called HAD-SST,
And did it match up?
It matched up really well. The correlation was very strong, 0.91, where 1 would be a perfect match.
Wow, okay. That's pretty
It
convincing.
gives them a lot of confidence that the variations they see in the Circuit ratio further back in time really do reflect changes in ocean temperature.
Okay, so they've got this validated centuries-long temperature record from these Caribbean sponges. What does it actually show? What's the big picture history?
Well, the big picture is this amazing continuous record of ocean mixed layer temperatures stretching all the way back to the year 1700.
300 years. So, using that record, what do they consider the stable pre-industrial baseline before humans really started changing things?
Looking at the sponge data, they found periods where the temperature was remarkably stable, like varying less than 1/10 of a degree Celsius per decade.
When were those periods?
From 1700 right up to about 1790, and then again after a dip from around 1840 to the early 1860s.
So those stable times, especially that long early stretch from 1700 to 1790, that's what this study uses as its reference point for pre-industrial.
Essentially, yes. That period, combined with the stability after the volcanic period, represents the baseline ocean temperature state before industrial warming really took hold, according to the sponge record.
You mentioned a dip between those stable periods in
Yeah.
the early 1800s.
Yes, exactly. And that dip is fascinating because it lines up perfectly with known major volcanic eruptions that had global cooling effects.
Like Tambora.
Pambora in 1815, definitely. But also others like Luigi in 1783, an unknown eruption around 1809, Cosigina in 1832. The sponge record clearly shows a cool period in the ocean mixed layer between about 1808 and 1828.
How much cooling did the sponges register?
About 0.2 degrees Celsius cooling in the Caribbean OML during that time. Now, the ocean has huge heat capacity, so it wouldn't cool as dramatically or quickly as the atmosphere.
Right.
But the fact that the sponge clearly records this known global cooling event is really important. It validates that the record is sensitive to these large-scale climate forcing.
That's a great reality check for their method. Okay, so stable pre-industrial temps in the 1700s, then volcanic cooling, then temperatures recover and stabilize again in the mid-1800s. According to the sponges, when does the warming trend really begin?
And this is the crucial finding. The Sclerosponge record shows sustained warming starting in the mid-1860s.
Mid-1860s, that sounds...
Early. It is early compared to when we often think of the signal emerging clearly in the instrumental records. It's significantly earlier than the start of widespread, reliable instrumental temperature data collection.
How much earlier are we talking compared to, say, estimates based on those ship temperature records?
The study suggests it's over 80 years earlier than when industrial warming seems to clearly emerge from noise in many analyses of those early instrumental sea surface temperature SST datasets.
80 years.
Yeah.
That's a massive shift in the timeline. So if the sponges say warming started mid-1860s, but the baseline often used, like by the IPCC, is later, say 1850, 1900, how does that work?
Well, that's the core issue the study tackles. It highlights this discrepancy between the sponge proxy record and the early instrumental SST records, particularly during that 1850-1900 period.
What was going on with those early ship measurements? You picture sailors throwing buckets over the side, right?
Pretty much, in the very early days. And that method itself changed over time. But the bigger issues were, first, very sparse geographic coverage. You can't get a truly global picture from just a few shipping lanes, especially missing huge areas like the Central Pacific.
Okay, patchy data.
And the data itself was noisy.
Yeah.
The study describes it as having roller coaster variability in that early period.
Roller coaster.
Yeah, like the instrumental record sometimes shows unusually warm periods, maybe from 1850 to 1880 perhaps, because the few measurements they had happened to catch more El Nino events, followed by apparent cooling into the early 1900s.
Okay.
Plus, there were known biases, like the shift from measuring water temperature in buckets, which could cool through evaporation, to measuring the intake water for the ship's engine, which could be artificially warm.
Different methods giving different results.
Exactly. And even biases between different countries' measurement practices, especially noticeable around World War II. So those early instrumental records, particularly before the mid-20th century, have known limitations and inconsistencies.
Okay, so noisy, patchy, biased early data. How does that relate to the sponges?
It helps explain something called the warm land, cool ocean problem. If you use that 1850-1900 period from the instrumental record as your baseline, then ocean temperatures in the early 20th century appear cooler by about zero point 0.3 degrees Celsius compared to land temperatures, and that apparent gap persists. But physically, you'd expect land and the upper ocean to warm somewhat together in response to greenhouse gases.
So it looked like the ocean was lagging weirdly behind the land.
Kind of, yeah. But the sponge data offers a solution. It shows the ocean mixed layer was actually warming consistently from the mid-1860s, right alongside the land warming trend that we see starting around then.
So the apparent cool ocean in the early 20th century instrumental record wasn't real cooling. It was just that the 1850-1900 baseline had already experienced some warming.
That's exactly the interpretation this study supports. The instrumental baseline started too late, after warming was already underway according to the sponges.
So the sponges basically argue for pushing the pre-industrial baseline earlier to that more stable 1700-1860 period they identified.
That's the core argument regarding the baseline. They suggest that while for practical reasons, modern climate data is often referenced to a period like 1961-1990.
Right, a standard reference period.
To understand the total warming since the true pre-industrial state, as indicated by the sponges, you need to add back the warming that occurred before that standard reference period began.
And how much warming was that, according to them?
They estimate that about 0.9 degrees Celsius of warming, plus or minus 0.1, occurred between the mid-1860s onset shown by the sponges and that 1961-1990 reference period.
Almost a full degree.
Yeah. So basically they're saying the traditional way of measuring total warming might have missed almost a degree that happened relatively early on, simply because the reliable measurement started later. To get the full picture, you have to account for that earlier start shown by the sponges.
Okay, that reconceptualization makes sense. It's not changing the rate of recent warming, but changing the total accumulated amount by adjusting the starting line. So, with this adjusted view, what does the sponge record tell us about the pace of warming over time?
Sponge data. First, that early industrial phase from the mid-1860s up to the early 1900s.
Okay.
During that time, they saw about 0.3 degrees Celsius of warming happening at a rate of roughly 0.09 degrees per decade.
Then the second phase.
That runs from the early 1900s to the early 1960s, the mid-industrial period. Another 0.3 degrees or so of warming, but the pace slowed down a bit to about 0.04 degrees per decade.
Interesting, a slowdown. And then the modern era.
From the mid-1960s onwards, and that's when things really take off in the sponge record. The rate jumps up significantly to about 0.15 degrees Celsius per decade.
And that acceleration lines up with?
It lines up very clearly with the rapid increase in atmospheric CO2 concentrations that really started accelerating around that time.
Did the study say anything else about the CO2 connection? Something about sensitivity changing?
Yes, there was an interesting observation. They noted that the amount of warming observed in the ocean mixed layer for each increment of CO2 increase seems to have decreased since the mid-1980s.
Decreased? How so?
Well, comparing 1964, 1984 to 1985, 2020, the warming per 10 parts per million increase in CO2 roughly halved. It went from about 0.17 degrees warming per 10 ppm CO2 down to about 0.08 degrees per 10 ppm.
Why would that happen?
They suggest it might be related to changes in the ocean itself, perhaps the mixed layer getting deeper in recent decades. If the heat is being mixed into a larger volume of water, the surface temperature rise per unit of extra heat might be less. Needs more research, but it's an interesting point.
Okay. And what about the difference between land warming and ocean warming?
The sponge data reinforces what we see in modern records, too. Initially, from the mid-1860s into the early 20th century, land and the ocean mixed layer seemed to warm more or less in tandem.
That changed.
Yes, the rates really started to diverge later in the 20th century, especially from around the 1980s or 1990s onwards.
How much divergence are we talking?
Land air temperatures are now warming almost twice as fast as the surface ocean temperatures, comparing the period since the 1990s.
Wow, twice as fast.
And that fits with what we see happening on the ground. Right? Amplified warming in the Arctic, permafrost thawing, more intense heat waves, droughts, wildfires. These are predominantly land-based phenomena exacerbated by that faster land warming. The ocean is acting as a giant heat sink, slowing the surface warming there relative to land.
Okay, so sponges give us an earlier start date, a revised total warming, show these phases of warming, and confirm the land-ocean split. Let's get to the bottom line.
Right.
What does this mean for the total warming we've already experienced, And where does it put us regarding those crucial climate thresholds?
Right. So if you accept the sponge-derived 1700-1860 period as the true pre-industrial baseline,
The starting point.
the study estimates that global mean surface temperature, or GMST, that's the blend of land and ocean temperatures, had already gone up by about zero point 0.9 degrees Celsius, plus or minus zero point 0.1, by the time we reached that standard 1961-1990 reference period.
Okay, zero point 0.9 by 1961, 1990. What about more recently, like the year 2020?
Using that same sponge-informed baseline, their estimate is that by 2020, global warming had already reached about 1.7 degrees Celsius, plus or minus zero point 0.1, above pre-industrial levels.
1.7 degrees Celsius.
Yeah.
By 2020, that really is significantly higher than the number we usually hear, which is around 1.2 degrees for 2020.
It is. It's about half a degree higher. And again, that difference comes almost entirely down to the baseline definition. The 1.2 degree figure typically uses the 1850-1900 instrumental period as pre-industrial.
Whereas the sponges say about half a degree of warming already happened by the time that period even started.
Exactly. So the 1.7 isn't saying the rate of warming in recent decades was faster than we thought. It's saying the total accumulation is higher because the clock started ticking earlier.
Okay, so if we were already at 1.7 degrees by 2020, what does that mean for the 1.5 degree target that's so central to climate policy?
Well, the implication is quite stark. It suggests that the opportunity to limit warming to only 1.5 degrees just by cutting emissions, that window has likely already passed.
Passed already.
Based on this sponge baseline, yeah.
Wow.
They estimate the 1.5 degree threshold was probably crossed sometime between 2012 and 2015, much earlier than other estimates suggested.
Wow. Okay, and what about the 2 degree threshold, the upper limit of the Paris Agreement goals?
Here, the projection is also quite alarming. At the current rates of emissions and warming, this study projects that the 2 degree threshold for global mean surface temperature will be reached very soon by the late 2020s.
The late 2020s. That's
Yeah.
potentially just a few years away. That's nearly 2 decades sooner than many previous projections based on the later baseline.
It is, and it dramatically underscores the urgency. The findings imply that to have any realistic chance of staying below 2 degrees, global emissions need to be halved by the early 2030s, absolutely no later than 2040, according to their analysis.
The challenge just got much steeper, much more immediate.
It really seems so. They also project that if things continue as they are, average land temperatures could be around 4 degrees Celsius above pre-industrial by 2050, with the global average, land and ocean, hitting 2.5 degrees in the early 2040s.
So these unassuming sponges, quietly growing in the Caribbean depths for centuries, they're basically telling us, hey, wake up. Warming started earlier than you thought. The total amount is higher. 1.5 is probably already behind us. And 2 degrees is approaching much, much faster than models using the later instrumental baseline predicted.
It's a really powerful example of how these natural climate archives, these proxies, can refine and sometimes really challenge our understanding, which has often relied heavily on the limitations of the instrumental record.
Absolutely. Which really leaves you, the listener, with something to chew on. If the starting line for climate change was actually drawn earlier, and we're consequently much closer to potentially dangerous thresholds than we assumed, what does that mean for how we respond, for the goals we set, for the sheer speed required?
And maybe also what other natural archives are out there. What other secrets might be hidden in corals, ice cores, sediments, maybe even other unexpected organisms like sponges, just waiting to give us a clearer or perhaps more challenging picture of our planet's climate story.